Okay, let's quickly recall what we learned so far. So we discussed the scope of models of distributed computing. We parameterized the models by the classes of faults they consider, from crash to omission to Byzantine, by the synchrony assumptions they make, from asynchronous to partially synchronous to synchronous, and finally by the communication media they assume, from shared memory. Well, in the most basic form, we assume read-write shared memory. You have the memory is a collection of read-write variables. You can write to them, overwriting the previous values, or you can read them without changing it. Or you can generalize these variables by assuming stronger primitives which combine reading and writing, like, for example, compare and swap or test and set. And then on the other extreme, we considered message passing models, where, for example, processes communicate over reliable channels. You send a message and you guarantee that the message will eventually arrive to its destination. Okay. And then we focused on one specific model, which is of particular interest for us. It's a model where processes communicate through so-called immediate snapshot operations, and it's nice because it gives us a very nice combinatorial representation of the scope of executions the model permits. And it's not too crazy to assume that this immediate snapshot exists, because there are implementations of immediate snapshot using just basic read-write variables. So basically, you can implement immediate snapshot, emulate it in software, and it's as good as implemented in hardware. Okay, so what is immediate snapshot? So we typically do something like this. Let me change the color quickly. So we have something like, let me keep it a little bit bigger. Sorry. Yeah, perfect. So in immediate snapshot, you have one operation, which we call, we combine with so-called immediate, we write immediate. So this is a pseudocode, so it doesn't correspond to any programming language, but let's assume that it exists. In this immediate operation, you can sort of write to the memory in your position. This is called for process PI. You write it your view, and then you take a snapshot. So you update your view as a snapshot. Let's write it this way. This is how we wrote it in the class of mem. Okay. So what's special about this computing model is that these immediate operations, they are executed kind of atomically, but they can be executed in parallel with other processes. So it's like groups of processes. They execute concurrently the write operation and the snapshot operation. Since they proceed in groups, they first all write and then all take snapshots. The results of these snapshots are identical for the group. Okay, and then you can model an execution where every process executes this immediate snapshot operation as a repartition of processes in groups. Okay, so you just basically it's a partition of processes in groups and putting them in a sequence. For example, for two processes, it's actually not very interesting because you essentially there are only two groups. You can either all go together or two partitions, or partition them in two solo groups, right? Except that you can change the order. Either they all go together, they both write and take a snapshot, or one process, let's say P0, performs a write and a snapshot, and then P1 comes and executes the write and snapshot, or P1 is the first one to execute a write and a snapshot, and then P0 comes and executes a write and a snapshot. Yeah, and it gives us a very nice combinatorial representation, but it's not coming from the snapshot. It's actually the same with regular read-write registers. So if you're because for two processes, you're only interested in the value of the other process, and that taking a snapshot is equivalent to performing a read operation. But in a combinatorial sense, we represent it as like this, right? We started with two processes being in some particular state. Yeah, so this is my initial state. And then once they finish their computation, they can be in one of two possible states. So this is for P0 running alone, this is P1 running alone. And then P0, P1, and P0, P1 seeing each other. That's how I represent the state. They both see each other. So this is the snapshot outcome of this execution. So you have three executions. Yeah, three executions, and for example, a process P1 with the blue vertices correspond to process P1. In this case, sees both processes, and in this case, P0 sees both processes. Okay, so for two processes, it's pretty simple. And then we can consider any two. If we have three processes, P0, P1, P2, then we can sort of describe all combinations of views resulting in executions in which only two processes participate. So here, P0 and P1 participate. I can identically find something like this here, and I choose the red color for the for process P2. Yeah, so this is P2. And then I find the two views of P2 on the sides from P0 and P1. Yeah, so these are, if you want, maybe I will change it a little bit. Sorry, I changed the color. Oops, sorry. I'll change the color like this, and I will write everything in blue for the labels. Second. So this would be P2 only seeing itself. This one, and this would be P0 and P2 as P2 sees them. This is P1 and P2 as P2 sees them. Okay. And finally, we have these two views for P0 and P1. Again, P0 and P2 as P0 sees them, and P1 and P2 as P1 sees them. Okay, so this is here. What we describe here is 9 executions corresponding to the settings in which at most two processes participate. Okay, actually exactly two processes participate. So for example, if I take this particular execution, I can represent it as follows, as this. So you have P2, yeah, let's say you have 3 processes, but only P2 and P1 participate. So P0 is not taking any steps here. So you have P1, P2. Okay. So here P2 is the fast one. It executes its immediate snapshot like this. Yeah, write a snapshot. And then P1 comes and executes a write and snapshot. Okay, so this is this particular execution. Yeah, this one, for example, is the one where you have these two processes running together. So they both write and then take snapshots. Okay, so again, P0, P1, and P2. Okay. And all the rest are permutations of these two executions. Okay, does it make sense? So please, if you're confused or you want to focus on Zoom on some particular point, we have the luxury of doing this. And please take raise your hand virtually in Zoom, or write something in the chat, or enable your microphone and say something. Okay, so you're very welcome to do this, because this is it helps a lot in these online lectures. Yeah. By the way, I also make a recording, so at some point you can see the video of this. Okay, are we together? So here we described all executions in which exactly two processes participate. Notice, for example, that if I take a corner here, let's say for P2 cannot distinguish whether P0 is the guy who is running with him, or P2 is the guy or P1 is the guy running with him, because he only sees itself. Yeah, it's actually he took a snapshot before anybody has written. Okay, so this is for two processes. And now what we need to introduce is to introduce the third process in these two process executions. Yeah, and this gives us what? This gives us these three vertices in the middle. Why you have three vertices in the middle? Because we have three processes. Okay, and these three processes see everybody. These are the only two states. The only state, one state per process, which we are missing, is the state where the process sees everybody. Because in any execution, the process either sees only itself, or it sees exactly two processes, or it sees exactly three processes. Yeah, because there are only three processes. So in every execution, you have at most three possible views the process may get. Okay, so then we depict it like this. We have let's say yeah, I'll do it like this, like the process, the vertex for process P0, we have a vertex for process P1, and we have a vertex for process P2 like this. Okay, so now what's left is how to connect these vertices to other vertices in the system. Yeah, of course we have an execution in which they're all connected. Yeah, now we have three processes, so an execution in this three process system is modeled as a triangle. It's three views combined together. Yeah, this is a simplex, two-dimensional simplex. So this particular execution corresponds to the situation where all these three processes go together. Yeah, they all write and all read. Okay. Now, we already have this execution here. For example, P0 is absent, but P1 and P2 first writes and takes snapshot, and then P1 comes and takes a snapshot. Yeah, so we can always extend it with two steps of P0 without affecting the views of P1 and P2, where P0 is the last one to write and take a snapshot. Okay. So remember, the beginning of this corresponds to this edge here, and the end corresponds to this view of P0. Yeah, so we have this triangle here. Yeah, this one. I dash this to show that it's a solid triangle. It's actually an execution. Okay, it's a simplex in this simplicial complex. It's actually a protocol complex of one round of immediate snapshot. Yeah, so far we depicted two executions in this simplicial complex, so two simplices in this simplicial complex. Okay, now we also have this execution here, this situation where P1 and P2 are coming together and they only see each other. We can extend it with two steps of P0 and connect it to this vertex. Yeah, so we have this one. Symmetrically, we also have this one. Yeah. And then we just extend. So this, for example, this one we didn't discuss. We have two full view states of P2 and P0, and the solo state of P1. So this particular execution, we can depict it like this. So we have P1 taking a write and a snapshot, and then P0 and P2 coming together, executing concurrently. So if you talk about the repartition of the system of three processes, this is the first, a singleton set for P1, and then the set of two processes for P0 and P2. Okay? And all the rest is just permutation of this. Yeah, so we can simply fill out all these remaining, sorry, this is wrong. You connect two vertices of the same color, not possible. This is, of course, bogus. No, that's this. Yeah, remember that an edge in this formalism of simplicial complexes corresponds to the, it means that the two views of two distinct processes can be observed in the same execution. Yeah, and the same vertex. I'm sorry, again, I made a mistake. Sorry. Yeah. Why nobody corrects me? You have this, and I dash all of them. Okay, just to make sure that we understand that all these triangles are the same. So an edge here corresponds to the an edge between two distinct vertices, means that the two views corresponding to these two vertices can be observed in the same execution. You have a simplex, which is a combination of vertices with the same meaning. A simplex means that this combination of views corresponds to an execution of your model. And these are the only 13 executions of your model, of the immediate snapshot model. Yeah, you cannot have anything else. So this can be formally proved. But intuitively, this is the case, yeah, because this corresponds to all possible permutations of partitions of my set of processes, 3 processes. Now, if I want to extend it to more processes, for example, I want to talk about 4 processes. Yeah, I can extend it, but I need more dimensions. Yeah, these 3 processes, P0, P1, P2, this would correspond to just one face of this 3-dimensional simplicial complex. I'm not going to draw it, but imagine that you have this is a face. So basically, I just draw it like this. I don't know, like this. Okay, I will draw it like this, and I put a dash line here because it's going to be hidden soon. And yeah, it's going to be like this: P0, P1, and P2. Okay, and then we also have P3 somewhere here, and I give it green color, for example. Okay. So this is my initial state. It's a tetrahedron. Yeah, it's a 3-dimensional object. And then I can run it for one round, and then I can, as I did it before, I can imagine that first only 3 processes, P0, P1, P2 participate, and P4 it sleeps for a while. It only comes after these 3 processes are done with their snapshots. And then what I have is something like this. Yeah, like as before, I had this subdivision here. Yeah, so you have all these 13 triangles on this face. Yeah. Okay. And the same way I can permutate the process identifiers and get the same subdivision on all these faces, all the rest of the all remaining 3 faces. Yeah, only 4 faces exist for 3-dimensional simplex. Yeah, 3-dimensional simplex has 4 faces because you have 4 processes. You remove one of them, and this is the remaining face. Okay, face sets, and I'm talking about faces of the largest dimension. Okay, and then inside, if I want to continue, I should plant a vertex for. Yeah, well, let me do this exercise. I think it's useful. I put inside. This is inside the tetrahedron. Right, this is the vertex for P3. Yeah, this is P3. This is P2, P1. This is P0, and this is P2. This is for P3, the green vertex. And what I have to do is to connect all these triangles on the face to this vertex, all the vertices. Yeah, because all of them correspond to the situation where they finish. Well, I'm not going to draw it, but it's like a lot of tetrahedrons inside. Okay. And then similarly, I can draw an internal vertex for P2, for P1, for P0, and do the same for the remaining subdivided faces. Yeah, the faces of the largest dimension. Proper faces, yeah. Again, because the a simplex itself is also a face of a simplex. Yeah, it's a subset of it, but it's just a stupid subset. Okay. This is how I do with dimension 3, and of course for dimension 4 and higher, I won't be able to draw it. Are we together? Is everything clear? Yeah, please react. Okay, thank you. Okay, so there's a. No, yeah, everything's fine. Yeah, thank you. Yeah, if you have questions, just yeah, maybe it's better if you enable your microphones. We are not that many. Okay. Now, we moved to a special class of tasks, which we call colorless tasks. Yeah, tasks which can be defined regardless of the process identifiers. Right. So for this class of tasks, the process identifiers are irrelevant because everything which identifies the correctness of the task solution is related to the inputs themselves. It doesn't relate to who proposed those inputs. And basically, the task can be defined as a map between the sets of inputs proposed by different processes, no matter who proposed them, but it's important that these sets are present. Two sets of outputs. Yeah, so you have maps, inputs to outputs, and you don't care who proposed what. And technically, it means that when you solve the task and you see that someone produced some output, you just come and take this output as yours. You can do this without affecting the task's correctness. Yeah. Same with the inputs. If you come with some input and you see someone proposing a different input, I can just sacrifice my input and take this process input as myself, as my own input, and this won't affect the task correctness for this execution. Okay. Good. So this is how we define a task, and we also consider a very exotic model of computation where we ignore identifiers. We only care about the sets of views. And this suits very well this immediate snapshot model, because in the immediate snapshot model, you take a view. Your view is actually a vector of views proposed in the previous iteration, right? And if you run together with a group of processes, you share this snapshot. Yeah, you have exactly the same vector of views. And then, yeah, what you do is you just look at these views, and you see identical views. You don't really care how many. Yeah, you just treat them as one view. So basically, you take a set of views. How we write it? Let me clear everything. So there is this special model of computation, which we called colorless layered model. I call it colorless layered model. Layered means that we have immediate snapshot memories provided in unbounded quantities in the ordered way. So we have one memory for the first round, another memory for the second round, the third memory for the third round, and etc. So it's just clean memory for every round of computation. In every round of computation, you basically take a snapshot. You write and take a snapshot. The only thing which makes it different from classical iterated layered model is that we ignore everything, but we only care about the views, not the who has these views. So how we do it? We have this shared memory array. Yeah, this is my memory. It's give me a second. Sorry. Yeah, it's an array of well, 0 to n minus 1, where n is the number of processes. Yeah, you have n positions in a line, and then you have sorry. We have L layers. Let me erase this one and write it differently. Like L minus 1, and you have 0 to n minus 1, where n is the number of processes. Now you have L rows, and in each row you have n columns. Okay, n positions in every row. So you as a process have an input, yeah, and this is how you initialize your initial view, yeah. And then for let's say j from 0 to L minus 1, you execute this immediate operation as we described it. Yeah, in this operation, the first thing we do, we write, yeah. In layer J, to position I, we write our view. And then we take a snapshot. Well, here I use a special variable, which is a snapshot of jth line in this two-dimensional array. Okay, we just take a snapshot. I just put star that we just atomically read all the variables in this line. Yeah, everything what other people might have written in iteration J of their iterated protocol. Okay. Now, once we get this, what we do is we set as a view, we set the set of values in snap. Yeah, so we understand what it means. Yeah, for example, if I have a vector which has, I don't know, 0, 0, 0, 1, 2, the set of values in this vector would be 0, 1, 2. Okay, so we don't really care that 0 appears in multiple times in these particular positions. We don't care. We ignore all this information. Okay. Finally, after we run this protocol for L rounds, yeah, what we do, we return delta of V. And delta is the what we call a decision map. Okay. This is how we describe this colorless layered model operationally. This is like a code, like a program, what we execute. Okay, so the part of this lecture is going to be how to represent a protocol complex corresponding to this particular operational description as a combinatorial structure, as a simplicial complex. Any guesses already what kind of simplicial complex we get? By looking at this, can you guess? What do we get? This is something we met already and discussed. What kind of simplicial complex it would give? Let's say one round of this. Let's say for L equals 1. What is going to be as a simplicial complex? I'm asking this question because I think you may be able to answer it. Because I just a slide before I described the simplicial complex corresponding to one round of the same protocol, except that in this protocol we didn't ignore the vectors. We treated each vector as a vector, not as a set of values. Yeah, so we gain more information.
You were referring to the subdivision, because
what we
I think
described before, like the figure I drew before, was called a standard chromatic subdivision. It's a specific chromatic subdivision where every vertex has a color, process identifier, and the combination of vertices is in execution of this. Yeah.
Better, can you hear me?
If you treat them as views without the process identifiers, combined as a simplicial complex, what it's going to be? Any ideas? It's also a subdivision, and it is a subdivision we actually met before. Okay, there is something on the chat. Ah, okay. Okay. Barometric. Barometric is a nice word. It's barycentric, yeah, but very close. Yeah, barycentric subdivision. It's barycentric because it's not surprising. Remember that these guys. Well, maybe I will draw it again very quickly. We have this. I'm not going to use colors, but I'm just imagine colors there, right? Because every vertex here has a color and so on. But you see these guys here, for example. Yeah, these are the views of two processes. Let's say P0 and P2. Yeah. So this is, but these are two different processes, but they have the same view. And we don't care the process identifiers. So for us, we merge this together as the same vertex. And what is this vertex? The vertex is where they both see P0, P2. Similarly here, these two, we identify them as two vertices, but is a one vertex in which both processes see P1, P2. Here we have these two, we have P0, P1. Similarly, all these vertices here, they merge to one vertex, which is the three views. Except that we don't treat the vertices as process identifiers. We treat them as views, assuming that we have three processes starting with distinct views. They have different input values. Because if they have the same input value from the protocol's perspective, is like the same vertex. We start at the same point. Okay, so far so good. And I'm sorry, I'm not reacting promptly to what you write in chat. Sorry. Yeah. Okay. Yeah, Joao, I couldn't hear you. I guess something is wrong with your microphone. I hope you hear me. That's more important. And maybe you can meanwhile write your comments and questions in chat. Yeah, good. Right. So what does it give? You identify these vertices, identify all these vertices and these ones. And of course, the guys in the corners, yeah, these are, I only see one view. So they stay in the same place because you cannot identify vertices corresponding to different views. Yeah, because the views are different. So you only identify. What does it give? If you identify all of this, what you get is a barycentric subdivision. You have one barycenter for each face. Yeah, these are all my barycenters. Yeah, for each face. Remember that barycentric subdivision combinatorially is represented as a set where the set of vertices are the faces of the original simplex. Yeah, every vertex is the face of the original face of simplex. Okay, and two vertices are connected with an edge if one of the faces is a subface of the other. And this is exactly what we're doing here, right? We connect this because yeah, this includes all the vertices. This, of course, too, and that's it. We have 6 simplexes. Good. So far, good. Why 6? Because 6 is a factorial number of permutations of 3 processes. That's it. Not more than that. Of 3 views, if you want, 3 distinct views. Okay, and this is exactly what we get from here. So it's you simplify the standard chromatic subdivision and get to a barycentric subdivision. And this is, you can show that this protocol gives us exactly this. It's not difficult to do. Okay, so this is our colorless layered model. And since we say colorless, we don't have to choose colors anymore. Barycentric subdivision is not chromatic. It's just a set of vertices without colors. What's important is the structure. Okay. And then we sort of discussed a specific task, which we called barycentric agreement task. It's actually called simplex agreement if barycentric, because we only focus with we'll focus on specific subdivision, but for generic subdivision, it's again, we can define the problem of simplex agreement as a generic task for a given subdivision, regardless what subdivision is. So what's important is that you have a subdivision of a simplex. If you have only 2 processes participate, you converge to a simplex in the subdivision of the corresponding phase of these 2 processes. Yeah. If one process participates, it remains in the same place because it's the subdivision of a point is the point itself. Yeah. If all 3 participate, then you converge on some simplex in the middle. But what's important that at the end, every process produces a vertex, such that all the vertices produced by the processes constitute the simplex in the subdivision. Because it's simplex agreement on the barycentric subdivision is a barycentric agreement. And it's going to be instrumental for some of the formal claims we are going to make. Okay. So far, so good. So what I'm going to do, I'm going to switch to the slides now, because I think basically this is what we recall. I'm just recalling what we discussed last time. And what I'm going to do, I'm going to go back to the point where we stopped last time. And that was the problem of barycentric agreement. Yeah, exactly. Barycentric subdivision. We recalled what barycentric subdivision is. Yeah, so I changed to the white lights. Right. I hope you see the slides. This is barycentric subdivision of two-dimensional simplex sigma. Yeah, this is how it represented. So ignore the colors; they are not important. The colors basically here correspond to the distinct views the process started with. Yeah, so if you want, you have yellow, red, and green view, and then here the view, for example, on this yellow-red face corresponds to the view which is a set of yellow and red. This is a set of red and green. This is a set of yellow and green, and this is a set of yellow, green, and red. Okay, all together. Right. So this is my barycentric subdivision. Each vertex is a face of sigma. Yeah. An edge is simplex is a set of faces ordered by inclusion. Yeah. So every two vertices in a simplex are related by containment. One is a subset of the other. Good. Barycentric agreement. You start as an input complex. You have some complex. In this case, we just treat it as a simplex. So we can generalize it to any complex, but because here, when you have a bunch of processes, but they can start at the same view. Yeah, because it's colorless. Yeah, the red and blue, they start at the same input you want. Yeah. At the end, they need to converge to some simplex, which is a subdivision of the simplex constituted by the views by the inputs. Here we have three inputs proposed. Yeah. This, and this. And here you add a barycentric subdivision of the face corresponding to the simplex. That's it. So your output on one of the simplexes here. Notice that, for example, red and blue, they started in the same view, but at the end of the computation, they split, they part. Why? Because in the computation, they took different steps at different moments of time. And as a result, red doesn't learn anything new in this computation. It was always faster than the other processes. Yeah, it performed an immediate snapshot and it didn't see anyone else except itself. Yeah, while blue actually saw the green one. Yeah, the blue actually saw the green one, and the green one saw the blue one, so they converge to the same point where they see each other. Okay, they see each other and they also see sorry, they don't see each other, they see the views of each other. Okay, and then they also see the view of red because this is the same view as the initial input of blue. And finally, yellow one is seeing everybody. Yeah, sees all the three inputs. Okay, so this is a legitimate output of this barycentric agreement task. Formally, we can define it as an input complex. It can be any complex. The protocol complex of this, the output complex of this task is the barycentric subdivision of this complex. Yeah, yeah. Barycentric subdivision can be done like on the simplex, or it can be done on a complex. It's not a big deal. Yeah, maybe I can just illustrate it, but just I think it's clear from the way I do it. But if you have a complex not consisting of more than one simplex, yeah, something like this. Yeah, what is the barycentric subdivision of the complex now? I have a barycentric subdivision of each of them. Yeah, so I have barycenter of each simplex in this complex. And that's it. So what's important here is that, for example, I'm sorry, again, sorry, this is like this. It doesn't exist. Yeah. So you have, for example, this face subdivided in a barycentric way shared by these two subdivisions. Okay, so we have barycentric subdivision of a complex as an output complex of the task, and barycentric subdivision as a carrier map for the task. Yeah, the task specification, because barycentric subdivision can be seen also as not only subdivision as a complex, but can be also seen as a carrier map. It takes a simplex and maps it to a complex. What is a complex? Yeah, it takes a simplex with a face, for example, this one. Yeah, as the output of this barycentric carrier map applied to this simplex, we have these two simplexes. Yeah, this is the barycentric subdivision of this face. That's it, not more than that. And that's it. Yeah, so you can see that this is indeed a barycentric agreement task. You start with a simplex and you end up on a simplex within the barycentric subdivision of this simplex. Okay, are we together? In fact, what we did so far, what I described here is in fact the protocol complex of this colorless computational model. And the protocol complex by construction solves barycentric agreement on whatever you offer. You offer this set of views, you get a barycentric subdivision of this set of views. As a set of all possible outcomes, but in any particular execution, you converge to one of the simplices in this subdivision, which is equivalent to solving barycentric agreement task on this simplex. Good. So you have a subdivision as a carrier map. Yeah, so any subdivision can be seen as a carrier map. So the other important observation is that if you have a huge scope of potential inputs, my input complex in the colorless task, input complex describes combinations of possible inputs. Now, what are the inputs the task allows the process to propose? Okay. Potentially, you can have way more inputs than processes, right? So if you have only n+1 processes, your system is n-dimensional. Then in your task, you don't have to consider simplices of dimension higher than n, because these simplices do not correspond to any execution. You cannot have, in a system of n+1 processes, you cannot have executions in which n+2 or more processes participate. As a result, in considering the barycentric subdivision, or barycentric agreement task, it's enough to focus on the skeleton of dimension n. What does it mean? You have a set of all possible combinations of inputs. In some of these combinations, you have potentially more than n+1 inputs. But in any execution, at most n inputs can be proposed. So it's equivalent to considering this n-dimensional skeleton of my input complex. Okay. In the same way, the output complex of the task is going to be n-dimensional skeleton, because you cannot produce in a system of n+1 processes, you cannot produce more than n+1 outputs. Of course, it must be an n-dimensional complex, and this is going to be n-dimensional complex because you take skeleton of dimension n of the input complex and then apply barycentric subdivision to it. Okay. And then you can treat the composition of this n-dimensional skeleton and barycentric subdivision as a carrier map. Yeah, you first take all faces of dimensions n or less, and then you apply the barycentric subdivision to it. Okay, and this is your task. This is the n-dimensional barycentric agreement task. And if you want to give you, if I can give you an example, again, the example is very simple. Let's assume we have potentially 3 inputs. Yeah, 0, 1, and 2. Yeah, whatever. We don't care what these inputs mean, but let's assume that these are the inputs. And we only have 2 processes. Yeah, so what does it mean? It means that the input complex is the one-dimensional skeleton of this. You can either have an execution in which you have 0 and 1 proposed. You have an execution in which 1 and 2 are proposed, because we have only 2 processes. We cannot propose more than 2 values in a system of 2 processes. And then execution in which 0 and 2 are proposed. Also, of course, we have executions in which only 0 is proposed, which corresponds to this vertex. An execution in which only 1 is proposed, yeah, by both processes, and no execution in which only 2 is proposed by both processes. Okay, so this is my input complex. I run one round of my colorless protocol. What I get a subdivision of this phase, and this phase. And this is my protocol complex, or the output complex of barycentric agreement task for one-dimensional systems, yeah, with 3 inputs. So any simplicial complex corresponding to systems of 2 processes is a graph. This is a graph, right? It's a graph of I don't know how many 6 vertices connected in a ring. Yeah. Now together, are we good? This is for 2 processes. I just take this is the only thing which the only effect the dimension of the system can have here is the fact that I just take this simplex, this is the skeleton of a specific dimension of the input complex. That's it. So far, so good? Okay. Now, immediate snapshot protocol. Well, let's forget about Colorless so far. We have the immediate snapshot protocol. It solves n+1 process barycentric agreement task for n+1 processes. Yeah. On barycentric subdivisions. Yeah. So you have inputs coming from this input complex I. You have the skeleton of dimension n of this input complex. You take the barycentric subdivision of the skeleton. And this is where you want to converge. You want to converge one of the simplexes of this. So this is the task I want to solve, and the model of computation I use so far is the classical colored chromatic subdivision provided by the immediate snapshot. It's the first theorem. Basically, it says that okay, I can approximate barycentric subdivision using simplify. Okay. All input simplices belong to the skeleton one. Immediate snapshot returns a set of input vertices, face of the input complex, and the faces ordered with each other. So this is what I barycentric agreement protocol is something like this. Yeah, the one process sees only itself, and I know blue process says this is itself and the red process, and the green yellow process is everybody. So all the snapshots are ordered and by containment. And this is so each face, each view is essentially a face of sigma. Yeah, and what we have is something like this. Basically, what I get is the ordered faces that give us a simplex of barycentric subdivision. So it's not nothing really spectacular here. It's just a simple observation from the fact that you use something like immediate snapshot. And you iterate it. You can iterate it many times. Here we use capital N, but I should probably use capital L rather like this L, because it's confusing to use capital N for the number of layers and small n for the dimension of the system. You have n processes, take n-dimensional skeleton of the input complex, subdivide it in a barycentric way L times. This is what you get. Yeah, so you start here, you end up in some simplex in the barycentric subdivision after 2 iterations. This is for 2 iterations. So you can, as we did simplex agreement on the 1 iteration of the colorless model, we can do it in any number of iterations. Right. So this is what we had for the 3 processes. Starting with 3 different inputs. So you have P, Q, and R capital as the process identifiers, and P, Q, and R small as for inputs. Now let's say capital P starts with small p as an input. And this we describe this 13 possible executions, and this is what we get. All these outcomes. Okay. This is what this is something we already discussed. So it's all possible orderings in which processes can take steps. And this is what they get as outputs. Yeah. And for the chromatic, as we started with, we have this possible sets of outputs. So remember, notice that I jump between chromatic and colorless. Here, I'm talking about classical execution where you treat every snapshot as a vector, not as a set. So this, again, there's no harm in repeating, but this is the same stuff I started with. Yeah, you have an operational view, all the set of executions, 13 executions. You have combinatorial view, the same 13 executions, but represented in a simple way. So here we have 3 executions, like we have this, it's a tree. And it says, the first, we started with this set of inputs. The first process to take a step, for example, here is a process P, which is followed by a step of process Q and followed by a step of process R, and this is what you get to be as the outputs. These are a set of outputs they have. P only sees itself, Q sees P and Q, R sees P, Q, and R. Yeah, and then, for example, you have P starting first and QR coming together. Yeah, QR, C, P, Q, and R, and P only sees itself. Yeah, this is a set of possible. So these are all combinations that we can. Right. And you can jump between operational and combinatorial, and this is what we usually do. Whenever we talk about the physics of computation, in a way, we talk about specific model of computation, specific operations of them. Yeah, we start with the operational view, typically, because it's easier. It's like a program we write. Combinatorial view is harder conceptually because it unifies all reachable views in one picture. But it's once we grasp it, once we understand it, and we can start using it. And using it gives us a lot of power because we treat all executions as like reachable by a system model as a geometric object, like an object embedded in space. And so you can treat them, you can look at it from different sides, you can reason about its connectivity, that we already did for consensus and two-process systems. Yeah. Consensus is about connectedness, whether two vertices in which different opposite decisions must be taken by the task specification are connected, whether they belong to the same connected component. And we do. No simplicial map exists for consensus. No decision map exists. So we cannot decide consensus at this point. We need either to continue running until these two vertices become disconnected, or we prove that this connectedness is preserved under iteration. So it's connected now, it's going to be connected forever. In this case, we just say consensus is impossible to solve. Okay? Are we together? Good. All right. Well, this is a side observation, but it's going to be useful. Imagine that you have two protocols, and like I, P, and C, and then we have another protocol, I prime, P prime, C prime, and with the specialty that the protocol complex of the first protocol is a subset of the input complex of the second protocol. Well, naturally, we can compose the two. Yeah, the composition is I P double prime, C double prime, where P double prime is essentially this part of P prime, which is results under applying P to I, and then P prime to the result of this outcome. And yeah, C double prime would be this, just the image of this composition on the I. Okay, so yeah, you just basically, it means that okay, I run my protocol, I stop at some point, I got a collection of views reachable by this protocol, and then I run a different protocol treating these views as inputs. Okay. Right. So the colorless immediate snapshot protocol for one layer is the barycentric protocol, the barycentric I, and then we should apply the composition to show that it holds for any number of iterations, any number of layers. So we have L layers of colorless immediate snapshot protocol. The protocol complex is going to be barycentric L iterated subdivision of the input complex. Yeah. Oh, L or N. It's rather an observation than a theorem, but as usual in mathematics, you need to prove every statement. So if you're up to it, you can look up in the book of Herlihy, Rashbaum, and Kozlov on combinatorial topology in distributed computing. So they have a proof for that. But again, it's not a big deal because as soon as we understand that the view a process gets after one iteration of this colorless immediate snapshot is a vertex of barycentric subdivision, and any combination of views is a simplex of barycentric subdivision, and everything comes automatically. Okay. One thing we remember, I hope we do remember, is that the geometric realization of a subdivided complex coincides with the geometric realization of the complex itself, and it's the same set of points. And because subdivision doesn't change the geometry of the object. You start with the simplex or complex, if you want. You apply barycenic subdivision or any kind of subdivision, stellar subdivision, standard chromatic subdivision. Embedded in space, you get the same triangle as before. What does it mean mathematically? It means that you have some connectivity properties defined on the original complex. The same connectivity properties hold for the subdivided complex. Why? Because connectivity, remember, the connectivity is defined on the geometric realizations. It's not defined on the combinatorial structures. The connectivity as we defined it is actually the existence of an extension of a continuous map of a sphere to a continuous map on a disk. So if you have some contour here, like some image of a sphere, you can feel it with continuously within the geometric realization. Or put differently, I can start with this image of a sphere, and I can using continuous transformations collapse it to a point. Which is not possible, for example, in a complex like this. If it's geometric realization like this, I can find some image of a sphere like this, which cannot be collapsed to a point, or it cannot be put differently, it cannot be extended to a continuous map from a disk to the geometric realization, because any continuous map from a disk should hit the problem here in the hole. Okay, so again, take a step back. Remember that connectivity is defined on geometric realizations. Ergo, it follows that the connectivity properties of a complex also hold for a subdivision of the complex. Okay, so the corollary to the previous theorem would be that the protocol complex for an L layers, sorry, I will have to change the letter, L layer colorless media central protocol, IPC, is N connected. Because if N process, assuming that I is N connected, so we always deal with N connected simplices. Okay, now we're together. It's been N connected under subdivision, the protocol complex remains being N connected. Important thing, since you cannot drop the connectivity using this specific protocol complex, this specific protocol, this specific model of computation, colorless media central. If you started with some connectivity, you will have to keep it. You cannot drop it down. You cannot make it less connected than before. And again, keep in mind that connectivity is bad for us. Well, bad for us as protocol designers, because we want to solve tasks. Connectivity means confusion. Connectivity means ambiguity. I'm connected to many other views, well, intuitively, I think, of other processes. I cannot, being connected to different views of the same process means that I'm confused. I cannot be sure in my execution, am I in an execution in which this process has view A, or I am in an execution in which this process has view B. Pushing it to, this is, I'm describing the graph connectivity, but you can push it to any number of processes. And that makes your life harder as if you want to solve a task, because solving a task usually means breaking the connectivity, breaking the ambiguity, reaching a view in which you are no longer confused. Okay, now we're together. Good. Okay, let's move on. Finally, we had all the ingredients together. So I will formulate the theorem, then we should have a small break because it's kind of tiring to talk to the black screen. We have this notion of continuous maps. Yeah, from geometric realizations of simplicial complexes. We have a notion of a protocol map in specific model. Yeah, this is Colorless model. We know that the protocol is a barycentric subdivision of the skeleton of the certain dimension of the input complex. Again, we only care about the skeleton dimension n if we have n+1 processes. Yeah. So we can argue that the task has a solution if and only if there is a continuous map from the geometric realization of the n-dimensional skeleton of the input complex to the output complex, carried by sigma, or by delta, sorry. Delta is these tasks. Okay. Do we remember what a continuous map is carried by means? Now I'll just recall quickly. Yeah, so what do we have? Carried. Carried, it actually relates continuous world to the, because continuous maps, they do exist, but they should just preserve some tasks restrictions. Yeah, and the tasks restrictions are delta. So it means that for any sigma in I, yeah, for any input complex, the geometric realization of f on the interior of sigma. Why geometric realization? No, sorry. It's not needed. Sorry. Of course, you take the geometric realization of sigma. Yeah, it's a set of points. It's a subset of the geometric realization of I, of the input complex. And then you map it by f, and you get a set of points in the geometric realization of O. This should be a subset of what? Of the geometric realization of delta of sigma. Yeah. So the outputs f produces is somewhat close to what the task is assuming. In this case, we say f as a map from, well, yeah, of course, I should have written skeleton. I'm sorry. This should be skeleton of dimension n of I. And f as a map from skeleton dimension n of I to, of course, geometrically, to O is respects the task specification. Okay. Notice this if and only if here, because it's a characterization. Characterization meaning that it has necessary and sufficient conditions. Okay. So, when you prove such theorem, you need to prove it in both directions. Direction if, saying that if there is a continuous map, then there is a protocol, and vice versa. If there is a protocol, then there is a continuous map. Okay, so the if dimension here, the direction is slightly more complicated, and it relates to the notion of simplicial approximation of a continuous map, which we proved, or we discussed last time. Okay, so I should suggest we have a 10 minutes break until, well, let's say 2:50, and then resume. But before we go to the break, any questions? Do you have anything to ask or to suggest? Again, if something is not working, it's not working. Yeah, you should let me know. Anything to say? Is there in the chat? Yep. Sorry. Okay. Everything is fine. You follow. You're not confused. Okay, so we have 2:50 for the continue. Good. So I pause the recording, and we resume in 10 minutes. Right. So we are back to the statement of the theorem. Yeah, if we just look at the theorem before we even go to the proof, we just look at it. Well, if you already have a protocol, imagine that you have a protocol that solves a colorless task using this layered colorless immediate snapshot protocol. By definition, it means that there is a subdivision of certain degree, a barycentric subdivision of certain degree, and a simplicial map. Yeah, remember that we described this protocol. I just draw this few lines of the pseudocode describing a colorless protocol. You run the immediate snapshot in a layered way for L layers, and then you apply the decision map. The decision map is simplicial by construction. Yeah, it's coming from the fact that it's applied to the vertices resulting after the running this protocol, and that's it. Of course, they map simplices to simplices. And the protocol itself, the L layered colorless immediate snapshot, it's L degree barycentric subdivision. So what do we have? We have L degree barycentric subdivision, sufficiently fine-grained. Every vertex of it is mapped to the output complex, to some vertex of the output complex, in a simplicial way. Yeah. And this is what we mean by solving task. Yeah, it's simplically mapped, and it's also carried by delta by construction. So this is what we get from the fact that the task is solvable. There is a protocol. A simplicial map can be trivially extended to a continuous one, defined on the geometric realization of the protocol complex, which is the same as the geometric realization of the input complex. Remember, subdivision preserves the geometric realization. How we extend a simplicial map to a continuous map? Using barycentric coordinates. Yeah, remember, we can just take any point in the geometric realization with simplex and represent it using geometric coordinates. And that's it. Yeah, you extend it basically from the points, from the vertices, you extend it to the interior of a simplex, to any point in this geometric realization. It's going to be continuous by definition. Again, it's going to if we do it for each simplex in the complex, each this extension agrees on the boundary. And it belongs to both shared space, and it agrees with neighboring simplex, and just extending it to every simplex in the input complex. You get a continuous map defined on this simplex. Yeah, there's I'm not sure how to interpret this message about Alex cutting mic. I don't know. I don't. Yokoyama, you can you explain what you mean? I do not hear Alex. No, I don't hear anyone actually. Okay. Okay. I see. I see. Well, I couldn't hear anything. Maybe I have some nice noise protection. Yeah. Yeah. Thank you. Good. Right. So this is one direction. And this is what we're going to see very soon. And the other direction is about simplicial approximation. We did this before. Simplicial approximation. How to approximate a continuous map using simplicial maps. And actually, you can approximate it with any mesh shrinking subdivision. We know that barycentric subdivision is mesh shrinking. We actually had a homework on this. Many of you actually solved it. How to show that barycentric subdivision is mesh shrinking, actually even giving a bound, how fast is shrinking mesh. Not very fast, by the way. It's pretty long, but it does. And yeah, so and then yeah, you can approximate any continuous map using mesh shrinking subdivision. It's not a big deal. In a colorless way. Yeah, colors are not very nice for a continuous maps. Continuous maps are basically about colorless computations. Well, there are some interesting suggestions how to describe colors of points in a continuum, and it's pretty funny. There are very interesting suggestions, but it's a bit peripheral. It's more like cutting edge of this theory rather than mainstream, which we do now. well, but it's kind of curious. Anyway, so far we stick to colorless, and actually I don't think we're going to have time before the end of the period to discuss colored computations. Colorless are already quite interesting. Anyway, so we move to the proof. Yeah. Sorry. Yeah. Actually, I have a discussion of this. I have a slide for this, and I already did it. Yeah. Let me remove all this. Sorry. I'll just remove all this because I already have the same thing here. This is good. This is what we mean by continuous maps carrying the carrier map of task specification. Good. Yeah, we start from the hard direction. So if we have a continuous map, how we get a protocol? Yeah. So there is a continuous map carried by delta. There is a weight-free protocols for blah blah. Well, the weight-free again. Weight-free is confusing here because I did define it, but it's not relevant. There is a layered protocol, colorless for this, and we recall what simplicial approximation is. We didn't prove it in detail. I think I hand-waved a little bit there, and I mentioned Lebesgue numbers there. Lebesgue numbers it's a mathematical tool of measuring the complexity of a topology. It shows sort of the minimal size ball which can be inserted in any intersection of open balls, something like this. Anyway, so yeah, the more fine-grained is the space, the smaller are the open balls, the higher is the Lebesgue number. But in any case, the Lebesgue number exists for any like a set of open sets defined as pre-images of stars of an alpha complex for a simplicial map. So it's something which is quite technical, but again, it's nothing really deep there. So what's important here is that if there is a simplicial if there is a continuous map mapping A to B, where A and B are geometric realizations of simplicial complexes, this thing here. Oops, so we have this. We say that there is a simplicial approximation of it, which is a simplicial map from A to B. I should say it again. I will keep saying it just to make sure that you grasp it. It's basically a kind of misuse of notation when I write it this way, saying that phi is the map from A to B, because a map from A to B, technically it's a map defined where A is a set of simplices, and B is a set of simplices. So it takes a simplex in A and maps it to simplex of B, but it's not really what phi is. Phi is actually a vertex map. It maps vertices to vertices. But since it's simplicial, it can also be seen as mapping simplices to simplices. So you feed to phi a set of vertices which constitute a simplex in A. The image of this set of vertices is going to be simplex in B. But technically, I shouldn't write it this way. It's just it's a short way of writing it. I should write it phi from vertices of A to vertices of B, a simplicial map. This is how I write it. Anyway, so if there is a continuous map from A to B, I will call phi to be a simplicial approximation of F if for every vertex in A, I take an open star of this vertex, which is a subset of the geometric realization of A. Open star is the interior of all simplices of A containing V. Remember that what is it? So you have I don't know, the set of simplices. This is V, for example. I take all the interiors of the simplices which contain V, and that gives me all these points here except for the boundary. These are the simplices which do not include V, so they are not included. Okay, so this is basically it's an open set in V, Euclidean space taken by A, which is next to V in the list. It's a neighborhood of V. Okay, so we take this, so we apply F to all these points. What we get is a set of points of the geometric realization in B. And the set of points should be in the open star of the image of F under phi. Sorry. You apply phi to V, you get some point, you have it's a point, it's a vertex in B, you take all the simplices which contain V, take all the interiors of these simplices. Yeah, what you get again is an open subset of B, of the geometric realization of B. And this open subset should include the image of F, an open star of B. So F is kind of more precise than C. Sorry, even phi is simply shown. So phi precision grasps everything that F does. Yeah. In this case, we say it's a simplicial approximation. Okay, so far so good. Right. So this is my definition of simplicial approximation. There is an alternative definition. Actually, I think I give it as an exercise to check this. So the other one is this for any simplex in A. So now I'm not talking about vertices, I take it as simplices. Yeah, I define the image of F on the interior of the simplex. Yeah, this is now well-defined thing. Yeah, we have the interior of the simplex. It's not the vertex anymore. It's not one point. This can be an interval or a triangle or a tetrahedron, etc. Apply F to it. What I get, I should be a subset of the intersection of open stars of all the images of vertices of sigma. Yeah, the intersection of all of them. Yeah, if sigma is V, yeah, you can kind of get a trivial statement. But if sigma is not V is a vertex, then it's trivial. But if it's not a vertex, then it's not trivial. It's a pretty restrictive thing. And yeah, so you check the exercises, and you have a problem with this, showing that these two definitions are actually equivalent. Okay, so this is what we mean by a simplicial approximation of a continuous map. The simplicial approximation theorem says that if you have a continuous map under certain iteration of n, we can approximate this simplicial map. So why do we need these iterations? What does it mean to iterate? It means that the continuous map itself can be, it's just a continuous map. It works with continuums. Yeah, take this set of points, dense set of points, and maps it to another dense set of points. And on the way, since it's continuous, it's only continuous, it doesn't have to be one-to-one. It can stretch or shrink the distances between the original points arbitrarily. And especially shrinking is very tricky for us. It can arbitrarily dense in this, so you have this A here, and you have B here. So this is my A, this is my B. And for example, I can take these points here, and they can all be mapped to this almost the same points here. Very, very close to each other, maybe even to the same point. So it's also allowed. So basically, you have a lot of like stretching, shrinking to do. How do you approximate this? Because you need to be able to make sure that the image of this is, or the other way, it can take all this small here and then map it to very large, sparsely large continuum here. So basically, what you need to do is somehow to take into account all this stretching and shrinking. And for this, you need to really be careful with the image, with the input of phi. So you should really to approximate it very, very carefully. The degree of approximation is actually relates to the shrinking and stretching factor of f, which is no way, by no means it's a fundamental definition, but it's just an intuition. So the more sophisticated f is, the more potentially you have potentially the more fine-grained the input for the simplicial approximation tree. The original input complex may not be sufficiently fine. Okay, so now we all have these ingredients. We take this simplicial approximation as given. Yeah, we know that we can approximate a continuous map, and that's what we're going to do basically. Yeah, we have a map, simplicial map. Oh, sorry, we have a continuous map defined on the input complex and output complex. Yeah, we approximate using the simplicial approximation theorem, using specific degree of the barycentric subdivision of map. The intuition behind this is very simple. The simplicial approximation is going to be the decision map of the protocol, and the degree of subdivision gives us the protocol. How many layers of the colorless barycentric subdivision or colorless immediate snapshot protocol we need to perform before we are able to map. We get sufficiently fine-grained, we get the points, the views of a process sufficiently close to each other, such that we can approximate the desired continuous map. Okay. You run barycentric subdivision, you get a simplex in the barycentric subdivision, you map it using phi. Yeah. And this is this is the output we're doing. Why is it good? Why would we solve the task? Because the simplicial approximation preserves the properties of the original continuous map. Remember that the original continuous map, I'll come a step back a little bit to the statement of the theorem. If there is a continuous map carried by delta, then its simplicial approximation is also going to be carried by delta. And this is what the solution of the task should satisfy, right? Should be carried by delta, it should respect the task specification. And this is something you need to prove in the exercises. Yeah. You can see the exercise to show that indeed one implies the other. The fact that the task, well, the continuous map you want to approximate is carried by delta implies the fact that the simplicial approximation is carried by delta. Okay, so the simplicial approximation theorem gives us the protocol and the simplicial map, decision map. If you want, you run the protocol, you get a view, you map it to the output complex, you get the output value. And the fact that the continuous map which you approximate is carried by delta implies that the simplicial map combined with the protocol is also carried by delta, which means that we solve the task. Okay. Exercises are very important. The next time we're going to have an extended session discussing the exercise because of this. These two facts. One fact is two alternative definitions of simplicial approximation. It's not a big deal. This one is important. This basically shows that you indeed solve the task. Okay, so this is the lemma proving the only if direction, only the if direction of the theorem of our characterization. So now we're gonna have to deal with the only if direction. Given the protocol, how we get a map. But this one is technical. Well, it's nothing conceptual. Because we can simplify, we can sort of extend. We start with something simple, we extend it to something complicated. Yeah, continuous maps are somewhat more complicated because they operate in larger spaces. We start with simplicial maps, we extend them to continuous. Yeah, we start with the protocol. Again, weight-free read-write, but in fact, it's a colorless, whatever, immediate snapshot protocol for the task. Then there exists a continuous map carried by delta. Yeah, how we show it? I'm sorry. The skeleton here is the dimension of the system. Yeah, maybe I should repeat it more often. The fact that you have skeleton means that you have n+1 processes, dimension, n+1 processes. So we only have to deal with simplices of the input complex of dimension n or less, because at most n+1 processes can participate in every execution. Okay, so why? Why is it true? The first thing we recall is that if we take a simplex and take its geometric realization, The geometricalization is what we call a convex hull of the vertices embedded in space in a finely independent way. Yeah, a finely independent means that no combination of them can be can imply the other one. Yeah, so it's yeah. If you have 3 points, you don't place it on a line. Convex hull technically is the set of points described as barycentric coordinates. It means that you take the vertices of the simplex and take the linear combination of these vertices with coefficients taken from in the interval 0, 1, such that the sum of these coefficients is exactly 1. So it's actually what we call a convex hull of on V0, well, whatever Vn. Here you have the dimension. Okay. Now, for example, you null one of the coordinates, you get something on the proper space. Yeah, that's it. Yeah. If you null all of them except one, yeah, you get the endpoint, one of the vertices. Okay. Now what's left is, since you have F as a map you can build F as a map from A to B, such that for any vertex, for any point in A, yeah, X being a point in A, yeah, X represented as a set of I, Ti, Vi, yeah, for some corresponding end of point, because any X in the interior of A belongs to some geometricalization, to the geometricalization of some simplex sigma, defined as a set of vertices V0 to Vn. Yeah, what's left is just to find the coordinate of X. There is a unique coordinates identifying X. So what we need to do is to define f of X as a sum of the same coordinates, but with the images of Vi under delta. Delta is, remember, delta is my decision map. And this is how you extend delta. So this is extend delta from whatever A to B to F from A to B. This is my extension. So far, so good. All together. Yeah. That's it. So your start with the barycentric subdivision, which corresponds to the protocol map. You run it for capital N layers. Let's call them L. This is L. This is also L. Just not to confuse ourselves. You have a map, a simplicial map, saying, okay, you run it for N L layers, and then you stop. You get a view. You map this view to the output complex, to some vertex in the output complex, and you're done. This is a decision map, should be carried by delta. Okay, meaning that carry the delta again. There's no harm in repeating. It means that for any simplex in I, delta composed with barycentric subdivision of, I should say, skeleton M. Fi, yeah, because yeah, we only deal with n process systems of barycentric subdivision of skeleton of degree L, skeleton N of I to, yeah, sorry, just 1 second, up to apply it on sigma. Composed altogether. Well, if I write it this way, then I don't have to write. Sorry for a bit messy. I don't, because I write it this way. I don't need to write this. I can. Let me. It makes sense because you only have n processes, so I will write it directly this way. I think it's better. In skeleton N of I, because you have n plus 1 processors, you take some set of n plus 1 inputs at most of sigma. Yeah, this give me a subcomplex of the output complex, and this should be a subset of delta sigma. Okay. So this is my protocol complex, this is my decision map. This is my input sequence. So whatever I produce should respect the task specification. Okay. I keep repeating what I already have on the slide. Yeah. So this is what it's carried by delta, and we take the f as the simplicial extension or the continuous extension of delta. Yeah. So this is how we define it. It's defined on this to this. Yeah. And let me remove all this noise which I have here, just to make sure we don't confuse ourselves. Okay. By construction, since it's extension, we have this. Okay, which means this f is carried by, and this is exactly what we need to do. Yeah, we started with the existence of the protocol and we find the continuous map, which is carried by that. Okay. Here we use the second definition. This is we use the second definition of carried by delta, and there is a homework exercise showing that the second definition is equivalent to the first one. The first one defined on the open stars is more intuitive. The second one is more complicated, but it's easier to prove, easier to use in the proof. Sorry, it's more instrumental. Okay. So far, so good. So we mapped continuous to simplicial and simplicial to continuous. So 2 dimensions, 2 directions, sorry, imply the characterization. The theorem which characterizes the solvability of the task in the colorless task and the colorless media snapshot model. Okay, so it may sound a little bit abstract now, but you will see that it's not too complicated. It's just we need to get used to this idea that okay, you can abstract away everything which relates to the actual computing model. Now, this is something which does not have any real interpretation. It's just the existence of a map. But the fact that the map exists gives us a lot, and the fact that the map doesn't exist also gives us a lot. The fact that the map exists shows us that the problem is solved, is solvable, can be solved. The absence of such a map, the existence of such a map, shows that the problem is impossible to solve. And this is something which we're going to use to illustrate this theorem now. Yeah, so we're going to use it in the context of what we call case-set agreement and possibility. So remember, we discussed set agreement. Now we discuss case-set agreement is just like a small generalization of case-set of set agreement, where we have we discussed set agreement. Remember, for in the exercise, like for specific model of computation or for spacing set, we showed that okay, set agreement can be solved, consensus cannot be solved. But in fact, consensus and set agreement are both special cases of what we call case-set agreement, where we set inputs. Now, in this case, we have 3 processes having distinct inputs, 19, 21, and 32. At the end, they need to converge to some outputs. The outputs should be subsets of the sets of input. Yeah, we started with this, we ended up with this. And the size, the cardinality of the set of outputs shouldn't increase k, shouldn't exceed k, should be k or less. That's why it's called case agreement. So if k equals 1, this is consensus. We all agree on exactly one output, exactly one input, sorry. The output should be one of the inputs everywhere, the same input. Case agreement allows you to disagree. You can disagree, but not too much. Yeah, you cannot disagree more than k. You cannot produce more than k distinct outputs. So the theorem is going to say that you have n processes. Remember that notice that the larger k is, the easier it is to solve the task, the more degrees of freedom you have. Definitely, 2-set agreement is easier to solve than consensus. And remember that, for example, the set agreement, which can be solved in the model of computation of participating sets, like what we discussed in the homework, is giving us is solvable, but the consensus is impossible to solve. So yeah, any solution to consensus solves all k set agreement for k more than one, yeah, but not vice versa. The theorem is, this is an impossibility proof. This is one of the fundamental results in the theory of distributed computing. Basically, this is where people realize that you need some form of combinatorics to prove statements in distributed computing. Nobody managed to prove the theorem otherwise, yeah, using other tools. In one way or another, all the alternative proofs boil down to what we're going to see very soon, which is called Sperner lemma, which is a combinatorial tool, and which is using essentially the characterization theorem we just had discussed. What the theorem is saying: no layered immediate snapshot protocol can solve set agreement. Have n+1 processes. They cannot get rid of even a single input in the output of the set agreement task. Yeah, so you have n+1 inputs. You cannot produce a set of outputs of size n or less in all the executions of the immediate snapshot model, right? You can say, oh, in some executions probably you can, but there's always, no matter how you try, no matter what protocol you take, what decision map you choose, there will be always some execution in which, starting with n+1 inputs, you produce n+1 outputs. Okay, this is what we're going to prove. This is called impossibility of set agreement. Any questions on the statement of the theorem? Okay, so I'll recall a specific lemma, which is it's one of the fundamental results in mathematics. Actually, it's actually one of the most popular and widely used tools in mathematics. It's called Sperner lemma. And it's based on the notion of Sperner coloring of a subdivision. It's not, doesn't have to be even subdivision, it can be any protocol, any simplicial complex, which is manifold, but it's not important. Let's take a subdivision. What is Sperner coloring? We have a subdivided simplex. Okay, take a simplex subdivided. On this subdivision, we choose distinct colors for the endpoints of the original simplex. Okay, this is a condition of the Sperner coloring. So basically what we need to assign colors to every vertex of this subdivision in a specific respecting certain rules. The first rule is the corners have distinct colors. Yeah? Corners have n-dimensional simplex. You have n+1 distinct colors for the endpoints. Okay, so far so good, right? Take any face of the original simplex. Okay. For example, take one-dimensional faces. Yeah, one-dimensional faces of the original complex. Original simplex. Simplex is yeah, we take a simplex, but you can extend it to any complex. The colors of the face of the vertices in the subdivision of a face should be subsets of should belong to the colors of the corresponding endpoints. Yeah. For example, if I take this side here, I can only take red or yellow as colors for the vertices in the subdivision of this face. If I take this face, red and green, and subdivide it, the vertices of the subdivision can only be red or green. Respectively, the vertices here should be green or yellow. Okay, it doesn't have to be this way. It can be, for example, I can take both of these to be red or both of these to be yellow. It's just important that the colors here belong to the set of colors of the corresponding corners. Okay, and we extend this principle to any face. For example, if I take an interior vertex, which belongs to the subdivided face of three colors, yeah, yellow, red, and green, they can have any color of it. Okay. Okay. So you take the boundary of the face, and yeah, you take these colors, and this. Yeah, that's exactly what we. It's basically it's like an inductive definition. You take the interior, the vertex, which belongs to a face, and you consider the colors of the vertices on the boundary of this face, and the interior should take any of these colors as colors. This is called Sperner coloring. Now, if you look at this Sperner coloring here, right, we can observe that it actually has simplices. Well, in this particular case, simplices which have all three colors. Yeah, it's a two-dimensional simplex as a region, so you have three colors. The Sperner coloring is the number of colors used is necessarily n+1 for an n-dimensional simplex. So here we have two-dimensional simplex, we have three colors, and there is necessarily at least one simplex. This is Sperner lemma, but in this particular case, I can show you that there is a simplex having all three colors. Yeah, this one. Yeah, the interior simplex here has colors yellow, red, and green. Now you may say, okay, oh, it's just because we chose the colors in this particular way. And I would say no. No matter how you choose these colors, yeah, there will always be some simplex which has all three colors. Yeah, for example, I can say, oh, no, I can maybe have this red. Yeah, I can do this. Yeah, this way you have only two colors in this simplex, but then I have all three colors here. And then say, oh, no, I take and maybe make this green. Right, so you have only two colors here, but then you have three colors here. And in fact, what we're going to prove, there will be always an odd number of fully colored simplices in every Sperner coloring. This is our statement. Does it make sense? Why do we care? Why we talk about the Sperner coloring? But if you look at this closely and recall the definition of set agreement, this is exactly set agreement. You have to choose one of the proposed inputs, and the number of inputs should be less than n+1. Because you have n+1 inputs potentially, but the number of outputs should be at most n. So you cannot have fully colored simplices. And Sperner coloring says there's always at least one. Actually, it says there's always an odd number of fully colored simplices, but the odd number starts with 1. Yeah. So the smallest odd number is 1. So at least one should have all n+1 colors, which violates the specification of set agreement. Okay, so I suggest we have another small break. And before the break, any questions? Anything to add to comment? You can use chat. You can do whatever you like. You can enable a microphone. Are we together? Do you follow what we discussed so far? So in the rest of this lecture, we're going to prove Sperner lemma. Yeah. In the eCampus page, you can also find a very amusing little discussion, actually little argument showing that Sperner lemma is actually equivalent to something you might have heard of, which is called Brouwer fixed point theorem. It's one of the basic theorems in mathematics. Again, it's very, very fundamental. It basically says that if you have a map of space to itself, continuous space to itself, there must be a fixed point. There must be a point which is mapped to itself. It's not continuous space, but a compact continuous space. And we deal with compact spaces, so we only have finite continuums. It's like I take a glass of water, I shake it, and I wait until it calms down. And when it calms down, I realize that there's one molecule of water which ends up in exactly the same point where it started. So this This is how you typically interpret Brouwer's fixed point. And then in the compose, there is a small document which shows that these two statements are equivalent. If you have Sperner lemma holds, then Brouwer fixed point theorem holds, and vice versa. Okay, unless you have questions, let us have like 7 minutes break until 3:40, and then we continue from there. Yeah, it's like 15:40, we resume. Okay, so sorry. Right. Let's move on. All right. So we defined what Sperner coloring is. We identified Sperner coloring and the solution of set agreement. Yeah, basically, well, kind of identified, because we can see that any solution to set agreement is actually Sperner coloring, because it respects the properties of Sperner coloring, that every vertex should have colors of the boundary of the corresponding face. Yeah, you have this vertex here. The boundary of the corresponding faces are these two vertices here. Okay, so you take the colors of this. You have this vertex here. The boundary of the corresponding face is this one. The boundary of this is this, like 3 intervals, and the corresponding colors are red, yellow, and green. So these interior vertices can have any colors you like. Okay, and then now finally we identified, we showed, okay, indeed, any solution of set agreement is a Sperner coloring. Yeah, the Sperner lemma says in any Sperner coloring of simplicial complex, or in this case of the simplex, at least one n-dimensional simplex should have all n+1 colors. We call such a simplex fully colored. Yeah, well, here you have exactly one. But in fact, you can show that it's always an odd number. And you're going to have an even number. It should be odd number. Actually, it's instrumental, because we're going to prove this Sperner coloring thing by induction on n, on the dimensional system. You start with degenerate 0-dimensional simplex, which is a one vertex. One vertex has one color in Sperner coloring. And it's also fully colored, because it has exactly n+1 colors, n equals 0 for one vertex. Okay, so this is the base case is trivial. But I'm also suggesting to discuss the case of n equals 1, because it's more fun, it's less boring. We could start with just base case as it is, but I think it's also important to consider n equals 1 before we move to abstract n. We have 2 base cases for n0 and n1. Okay, so this is my inductive step. Yeah, I want to claim that for each k from 0 to up to some capital N, actually it should be small n, I guess, because we also use n. The face 0k. Yeah, remember we have n-dimensional simplex. It has faces, yeah, from 0 to well, it has vertices from 0 to n+1 vertices. You have a face which can be identified with 0 to k, vertices 0, 1, 2, up to k. Yeah. You want to prove by induction that for each k should contain an odd number of k-dimensional simplexes color 0k. Yeah, so of course, Sperner coloring, if I take a face 0k and subdivide it, the vertices of the subdivision should have colors from 0 to k, yeah, because it's Sperner coloring. Okay. Again, let's take a step back. We have a simplex based on vertices 0 to n. We have a Sperner coloring of a subdivision of this simplex. Yeah, so you have some subdivision, subdivide it, assign Sperner coloring to it. Yeah, every vertex has a color. You have n+1 distinct colors. A face 0k subdivided can only have colors from 0k. Yeah, this is by definition of Sperner coloring. Now, I want to claim by induction on k, yeah, from 0 to n. Yeah, when I reach n, I'm done because I'm proved my statement. Yeah, but I want to proceed by induction. I want to prove that phase 0k contains an odd number of k-dimensional simplices colored 0 to k, having all k plus 1 colors for the k phase. Okay, now we're together. K equals 0, trivial. Yeah. Exactly one vertex is there. By Schörner coloring has exactly one color, fully colored. K equals 1. K equals 0, so we have k plus 1 colors. Good. More interesting thing, k equals 1. What k equals 1 corresponds to, it's an interval, subdivided interval. How do we know? The endpoints of the interval have different distinct colors. Yeah. The interior should have an odd number of fully colored intervals. Yeah, you have, for example, you have the interval 0, 1, the endpoints have distinct colors, red and white, and you have a certain number of intervals in the subdivision. Now, I can have all color, any of these two colors in the subdivision, but I always claim that there must be an odd number of intervals colored red and white. How do we argue this? I say simple counting, but why is it true? Why it should be odd? Why it cannot be even? Of course, it should be. We should have at least one, yeah, because at some point we need to switch from red to 1. If you go from red to 1, at the end point it's from red to white. Sorry, at the end point you started from the endpoint colored red. The other endpoint should color 1. So when you travel from 0 to 1, you should at some point switch to a new color. Yeah, let's say 0 is red and 1. 0 is red and white is 1. If you go from 0 to 1, you should switch to at some point. You should have at least 1. But how we argue that should be odd? Anyone? It can be 3, it can be 5, but it cannot be 4, for example. I think I put you all asleep, no? Yeah, okay, Kaspar. There is an even number of colors. Switch from 0 1. 1 should be red. Why? Why it should be red? Strange, I don't hear anyone. You don't have your mics, or is there something wrong on my side? Yeah, again, if we switch even number, it means that you came back to the same number you started from, right? So if you go from 0 and you switch in even number from 0 to 1, you end up at 0, but you should end up at 1. So it must be even number, but it must, so the number of switches from 0 to 1 should be odd. A switch here means that you have an interval containing both colors. That's it. Yeah. I think I cannot hear you. I don't know. I didn't hear anyone. I don't know why. Oh, now I know why. Sorry, it's my side. I forgot to enable my my speaker. Yeah, sorry so much. Yeah, it's my side again.
So can you hear me now, Peter?
Yes, Raul, thanks.
Oh, great.
So it's been like more than 2 hours of lecture, and only now I noticed like hearing you. Sorry for that. Yeah. Anyway, so that's good now. So we have, this is a simple case of 1. And the argument is as simple as that. So we can extend it to any dimension by induction. So our induction step now is the claim holds for k equals let's say n minus 1. Yeah, and we consider the phase of all colors 0 n. Okay, so we have n plus 1 colors. Every phase of it satisfies the claim. Not every phase, but the phase 0 to k equals n minus 1 satisfies the claim. It has an odd number of simplices colored to exactly n colors. Yeah, and now we have n-dimensional phase with n plus 1 colors, and we're going to prove the claim for the n-dimensional phase. Good. I'm gonna illustrate it by using this language of doors and corridors and rooms. Yeah. So we have an n-dimensional simplex subdivided. Okay. It has an n-1. It has colors from 0 to n, but it has a face colored to the colors from 0 to n-1. So in this particular case, n equals 2. Yeah. So we have colors 0, 1, 2, and we focus when zoom on the face colored 0, 1. And we call, and remember that, okay, all the simplices here, all the vertices get colors from 0 to 2. Yeah, in this case, it's white, red, or blue. But some simplices, especially the ones which are n-1 dimensional, can be colored to all distinct colors from 0 to n, from 0 to n-1. In this case, from 0 to 1. Okay? And we call these n-1 dimensional faces doors. Yeah, it's like you can treat each n-dimensional simplex in the subdivision as a room, and this room may have a door. Okay? And in particular, by induction, we know that there are some what we call exit doors. Doors on the subdivision of this n-1 dimensional face 0, 1, or 0n-1. There, n is some abstract number. It's just this is just an illustration. It's not. It doesn't serve for the proof. It just illustrates it. Okay. Okay. So this n-dimensional simplex is a room. An n-1 dimensional simplex colored to colors 0 to n-1 is a door. Some doors are located on this side. Yeah. And remember that we proved by induction that a face from 0 to n-1 has an odd number of fully colored simplices. It's fully colored, meaning colored in the in colors from 0 to n-1. So put differently, there is already n-1 an odd number of doors on the boundary of the subdivided simplex. Notice that you cannot have exit doors on any other face. Yeah, because any other face has exactly colors from 0 to 2. And if you take any n-1 dimensional simplex on the subdivision of the face, you cannot have colors which are not on the boundary of this face. And so you cannot have an exit door there because you necessarily, for example, you take this face here, it should be colored 0, 2. No interval can have, no vertex on this subdivision, on this subdivided face can have color, for example, white. Yeah. So definitely there are no doors on this side. So there are only doors on the face 0, 1, or more generally, there are only doors on the face 0 n-1. Okay, are we together? So put differently, we have a subdivided simplex. We have some faces of this simplex. Yeah, all the vertices of the simplex have colors. We have some rooms inside, and the only doors which can allow us to enter the rooms inside are on this face 0 to n-1, and there are exactly an odd number doors. Okay, are we together? So odd number of doors. So we have a house with some rooms inside. Some rooms have doors, some rooms have no doors. It's okay. So it means it's a room with no doors. You cannot enter. But there are an odd number of rooms or doors entering, reaching the interior of this house. Okay. Odd number means exactly at least 1, 1, 3, 5, and so on. Okay. So each n simplex is a room. Each n-1 dimensional face, which is a subset of n-1 vertices, is of a room, is colored with all n-1 all n colors from 0 to n-1 is the door. Okay. Good. There is an odd number of exits. Let me correct a little bit. This is not very nice because a door is an exit if it's contained, if it resides on the boundary. Sorry, I just changed it a little bit. The boundary resides, because this is otherwise it's stupid what I wrote, because the next statement is kind of stupid. Yeah, so this is one. And finally, oh shit. Yeah. So the final statement is, yeah, the inductive statement is that there's an odd number of exits, because here all other faces, proper faces of the subdivided simplex, have no doors. Yeah, by the properties of Sperner coloring. Yeah, they cannot have all n colors from 0 to n-1 on faces other than the face 0 to n-1. And finally, by induction, exits can only be contained in n, and then by induction there are exactly odd number of these things, right? An odd number of fully colored simplexes in this subdivision. Good. So we have odd number of doors. Now, if we consider a room, interior room, a room is an n-dimensional simplex. Either there is one door, or there are two doors. Why? Why we cannot have more than two doors in an n-dimensional simplex in a room? So a room, either you end at the room, it's a dead end. You enter the room, you cannot get out, otherwise than going back. Or it's a passage. There are two doors. You enter and pass through another door. Why? Now I have my speaker enabled, so you can talk. So why you cannot have more than two doors, first of all? Well, it's obvious when you have a triangle with three colors, right? You have one door, and you have the third vertex. Yeah, one door is two vertices, white and red, and then you have a third vertex. It can be either white or red or blue. Can have any of the three colors. If it has the colors white or red, then you have two doors, right? Because you have now you can pair the remaining red. For example, it's white. You can pair the remaining red with this white or that white. So that gives you two doors. Or it can have the third color, which is blue. In this case, there's only one door because it is only one face colored in all colors, white and red. You can generalize it very trivially because you have n-dimensional simplex, which has one door at least. Okay, because we consider a room with a door. What is the door? A door is the face n-1 dimensional face of this n simplex, which contains all colors from 0 to n-1. Okay, so basically you have only one vertex, and you can assign a color to it. If this color is the remaining color n, the one which is not used in the door, it's a dead end. Yeah, there's only one door, right? Because any other n-1 dimensional face has a color, well, color n, which is not color of the door. So there's only one door. If it has one of the vertices, one of the colors between from 0 to n-1, yeah, then you have one more door, exactly one more door, because you take this n n-1 face, which includes now n-2 vertices, excluding this the color of the new vertex, and this new vertex, and this gives you one more door. Anyway, a room with a door is either a passage with two doors or a dead end, no other doors. Okay, now come back to the original understanding. So we have house with lots of doors on one side, yeah, on one face. It should be an odd number of doors to enter. Okay. Every room you enter has a door because you entered the room. And then there are two choices. Either you end up in a corridor, meaning that there's a passage, there's another door, you can go to another room, or you stop there because there are no other doors. So you cannot use the doors you already used. That's the rule. Okay, since there's an odd number of doors entering, yeah. What is the choice? You enter through a door, you go to another door, to another door, to another door. There are two possible choices. Since it's a finite house, you only have finitely many rooms. Either you end up in a dead end, yeah, you reach a room with all colors. It's a dead end, yeah. There's only one door in the room. It's one door, that means that it has all n colors, n+1 colors, sorry. Or you exit, yeah, leave the house through another door. Yeah, so you go through some sequence of rooms, and you leave the house. Okay, so this is what's happening here. Yeah, for example, in this case, you have like odd number of doors. Here it's 1, 2, 3, exactly 3, because every simplex here has two distinct colors. You enter here through this door, you go through this door, yeah, because you entered to a room which is passage, and you reached a dead end. You reach the room with only one door. A dead end is a fully colored simplex. Or you enter and you leave through another door. Since you have odd number of doors, either you have an even number of doors, which I use through passages, yeah, so you go and leave, yeah, you leave through a different door because you are not allowed to use the same door to leave. Yeah, then you have to remove the even number of doors which are like this. If you remove an even number from an odd number of doors, you end up with an odd number. Yeah, you subtract an even number from an odd number, you have an odd number. You have an odd number of doors which lead to a dead end, which gives us what? An odd number of dead ends in the interior. Okay, so the conclusion is the total number of fully colored rooms is odd in the n-dimensional subdivided simplex. Yeah, so by induction, we show that by assuming that you have an odd number of exits, you have an odd number of fully colored rooms or dead-end rooms in the interior of the simplex. Are we together? This is just one way to prove kernel lemma. There are many other proofs, but this is roughly the idea. So you prove it by induction on the dimension of the simplex. Any objections, by the way? So this is the point where I actually usually there's someone who says that, oh no, it's not exactly right. How do we conclude that there's a odd number of fully colored rooms? By the fact that you have odd number of fully colored rooms reachable from an exit door. Can we conclude immediately that there is an odd number of dead ends? Odd number of fully colored rooms. What's wrong in this argument? I think it's this analogy about a house with rooms is good. So you have odd number of doors, you enter, you pass through some doors, maybe you exit through another door, or you stay there inside in some dead end. Since you have an odd number of exits which lead to a dead end, I conclude that there is an odd number of dead ends. But is it necessarily correct? What do you think? What's not right in this reasoning? Okay. Well, you can talk now. I can hear you. Right. Yeah. Very good. Yeah. So here you assume that each. Sorry. What exactly assumes? Each exit door is linked to one exit door. Not each. No, it's not each. Some of them are linked, possibly, and some of them are linked to a dead end. But I want to conclude that since there is odd number of exit doors, there must be an odd number of dead ends. Is it necessarily true? What's wrong? It's not. It's really, the argument is correct, but I missed one step. Which step I missed? Let me give you an example. I just do this. Sorry, let me do this. What do I do? I will do this. Yeah. I will change the color of this to red. Okay. What can I say about this? Sorry, could you say again? You are not covering all exit doors necessarily, right? Well, exit doors, no, exit doors are here. You have, this is an exit door, this is an exit door, this is an exit door. I do cover all of them. Actually, I explore everything I can do from the exits. So it's not exactly what I mean by changing the color. What did I do by changing the color? I added some fully colored simplices here, which are not reachable from exits, right? Because this one is not reachable from an exit. From the exit, I can reach this one, yeah, this one. This is the fully colored one. Or I can enter here, pass through some passages and leave. So you have an even number of, I will call them corresponding doors which correspond to each other. Doors. And then you have odd number of doors leading to a dead end. Well, dead ends, not necessarily the same, actually, different ones. They cannot lead to the same dead end, because if two doors lead to the same dead end, then they correspond. Anyway, so this is, so I want to conclude that this is an odd number of dead ends, because there's an odd number of doors leading to a dead end. But by changing the color here, what did I do? It somehow breaks my logic. I say, oh, okay, you have an odd number of dead ends because there's only odd number of dead ends reachable from an exit, from exit doors. Sorry, exit doors. Number of exit doors, of corresponding exit doors. So it's about exits, not about all the doors in my house. Right, there are two dead ends which are not reachable from the. Basically, what I want to say there. Okay, I say there is an odd number of fully colored rooms reachable from the exits, but maybe there are fully colored rooms which are not reachable from the exits. So maybe with this, if I take these rooms into account, it's going to be the even number of fully reached, fully colored rooms, right? And this would break my inductive argument. I want to argue that there are an odd number of them. Is it possible that we have an odd number, even number of rooms which are fully colored and not reachable from the exits? What can I say about this? And for example, look at this example. What do we have here? Yeah, Yokoyama, you say there are two dead ends. It's an even number. Can you argue that if there are rooms which are not reachable from the exit and which are fully colored, there can only be an even number of such rooms? Specifically, it can be zero. Zero is an even number, which used to be the case before I changed the color of this vertex. And by changing the color of this vertex, I added two fully colored rooms. But can I argue that it's always even? This is what I want, right? You have an odd number reachable from exits and even number interior which are not reachable from the exits. Altogether, even plus odd gives you odd. Okay, what do you say? Think of doors of these rooms. You have some interior rooms which do not correspond to the exit. Yeah, they are fully colored. Fully colored means that they only have exactly one door. They have exactly one door, each of them. But having an exactly one door means that you can exit the room. You go to a neighbor room. Yeah, the neighbor room also has a door, at least one, the one which you used to enter. And you only have finitely many rooms in the house. So we almost there. What do we miss? Take this as an example. Yeah, you have this room here. Yeah, by the way, you can enable your microphones. Don't be shy. I have this room here. It has a door. This is the door. I can exit. I exit. I reach this door, this room. This is not a dead end because it has this room, this door, and this door. There's two doors. This is a passage. I exit. Again, this is not a dead end, it has a passage. It has this door to enter, this door to leave. I can go out. Since this is not reachable from an exit, by passing through door to door, from room to room, what do I have? At some point, I cannot reach an exit. So the only possibility for me to end up, because we only have finitely many rooms, right? You cannot enter back to the fully colored room because it only has one door and I can only use one door once. I cannot use the same door twice. So the only possibility for me is to reach another fully colored room and end up here. So I go from one dead end to another dead end. And this should be the case for any dead end which is not reachable from an exit. It has a matching dead end to which it goes. That's it. So you have like a series of passages in my interior, the interior of my house, which correspond to each other, but they don't lead to an exit. How many dead ends of this kind I can have? An even number, because they have each one has a matching pair. Even number into it. Okay. The conclusion. You have you have even number of fully colored rooms not reachable from an exit, and the odd number of fully colored rooms reachable from an exit. Altogether, you have an odd number of rooms fully colored. and odd is at least one, so at least one room should be fully covered, and Sperner lemma is proved. Okay, are we together? Good. Any questions? So the conclusion, no layered immediate snapshot protocol can solve set agreement. If the protocol exists, we run a layered immediate snapshot protocol, choose the value based on the vertex. Yeah. So you can choose the color. So the color is giving a Sperner coloring. So if Q and R take steps, they can only choose values of Q and R. If only P takes steps, it can only take its own vertex. This is Sperner color. And the interior can take any color. Okay. Any solution to n set agreement in the system of n+1 processes gives us Sperner coloring. But we know the Sperner coloring gives us at least one execution in which all n+1 colors are chosen, which is a contradiction. Okay, the Sperner coloring immediately gives us the impossibility of set agreement. And as I said already, recall that this kind of arguments can only be developed using the combinatorial approach. Nobody managed to do it otherwise. Those of you who took the class on distributed computing, distributed algorithms, might remember the impossibility proof for consensus, which is a special case of set agreement. K-set agreement. So K-set agreement with K equals 1. And there, the impossibility was operational. It was like proposed in 1985 by Fisher, Lynch, and Patterson, and they actually presented, explicitly constructed an execution in which no decision can be taken by using this language of balances. We would say, okay, oh, you have this particular state of your algorithm. From this state, certain set of decisions can be taken depending on how you extend this execution. And that would be a valency, and then we show that any consensus algorithm should have a critical state where you should decide what is next. Every next step decides the value, and then we show that critical configurations cannot exist in a synchronous system with failures. And that was way more complicated proof than this one, in a way. So that's the and this is a more general statement. So in a way, it's many people tried to generalize the valencies to K-set agreement and prove the similar statement for set agreement, or generalize the impossibility for consensus using valences, and it didn't work. Basically, operational approaches were not, at least nobody managed to do it so far, and it's kind of intriguing to understand why. And there are some people actually been thinking why is it true, and there were some results, some proofs that okay, certain kinds of statements require certain kinds of arguments, but it's still kind of it's very intriguing to understand why exactly this combinatorics helps us. Okay, any questions? This was the part of the lecture where we took some formalism, basically formalism based on combinatorial topology, applied it to a specific model of computation where we ignore colors, we ignore information about process identifiers. We took a specific model of communication, which is based on immediate snapshot. Yeah, we assumed a weight-free protocol in the sense that any combination of steps of n+1 processes is allowed. Yeah, and for this specific model of computation and this kind of communication, we proved that the specific task has no solution, using a more general characterization relating the existence of a continuous maps. Actually, it's not exactly application of this, but the intuition is very strong. What does it mean to be able to solve set agreement? Set agreement boils down to mapping a full n simplex, n-dimensional simplex of n+1 vertices with the interior to its n-dimensional, n-1 dimensional skeleton. So mapping a continuous disk to its boundary continuously is impossible. And this is basically it. That's actually all these Sperner things boil down to this simple statement. Sperner is exactly this. You cannot map a disk to its boundary in a continuous way. Okay, are we together? And this is exactly what set agreement requires. It requires mapping fully field triangle to its boundary, to a circle. Okay, so I will stop this. Okay, let me see my presentation and change the slides. Then go to solving colorless tasks in other models of computation. So basically, now we generalize all our results which we derived so far. We generalize it to a whole scope of different models of computation. And we restrict our attention to colorless tasks. I think it's already quite interesting. Okay, are we together? Good. And it's going to be all about skeletons. Skeletons, in the sense that the power of the model would actually boil down to the dimension of the skeleton it implies. First thing we observe is that we have n+1 processes. We have to deal with n-dimensional skeletons of the input complex, because there's no reason to consider simplices of higher dimensions because they are never observed. And no execution would start with such a simplex because we only have n+1 input stops. Regardless of how many inputs potentially may be present. Processes can take inputs from a very large space, but there are only n+1 of them. Yeah, you can only have n-dimensional simplices in your protocol complex. Okay. So we come back to the models. I will briefly review what kind of models we consider. Then we consider a generalization of the weight-free model we discussed so far, and we focus on T-resilient models. Models where everybody in the system of n+1 processes, at most T of them can fail. Yeah, and failing here means staying silent forever from some point on, not taking steps of the computation. Then we will discuss a model where it's still read-write. It's a layered snapshot model, except that we have at most T processes stopping taking steps. Yeah. And T is an important parameter. Yeah, the higher T, the weaker is the model. Yeah, the less things can be solved. If T is 0, for example, it means that everybody is correct. Nobody fails. Assuming that nobody fails, you can wait until everybody takes a move in real system. Yeah, because you know that nobody's stopping taking steps, so you just wait until you see inputs of everybody. If you see inputs of everybody, solving colorless tasks is trivial. Actually, not even colorless. Any task can be solved because you know the inputs of everybody. Remember the smudgy children thing. When you know the state of everybody, including yourself, everything is easy. Yeah. Any task can be solved in zero resilient model, n-1 resilient or n-resilient, sorry, for the system of n+1 processes where everybody but one process can fail. This is the weight-free model which we considered so far. So it's T-resilient is a generalized way of describing all the extremes. Yeah. No failures, to everybody can fail. And then we consider systems, we increase the power of the system, like we still stick to this model of immediate snapshot layers, but we increase the power of the model with some additional object, which we call case-set agreement object, where you can basically solve case-set agreement. So you can read-write, you can exchange communication using reading and writing, sorry. And then we can also access this case-set agreement by reducing the set of inputs to k. You started with potentially n+1 inputs because you have n+1 processes. Everybody has its own distinct input. At the end of the computation, you shrink the set of inputs to a set of k at most inputs using k-set agreement. Then we generalize this. We go to the notion of shared memory adversaries. Yeah, this is like it's a generalization of a T-resilient system where you say, instead of saying, oh, at most T processes can fail, you explicitly say who can fail. And because you may have a system where some processes are more reliable than the others, or you can have correlated failures. In this case, you're better use this language of adversaries. Adversaries explicitly define the sets of processes that can fail in an execution. You discuss the power of the adversary in solving colorless tasks by using specific characteristics of an adversary. Treating an adversary as a set system, it's a set of subsets of processes. And then the sets of subsets of processes, they have a core, minimal set of processes which overlap with all of them. And the size of the core defines everything, as we will see. And then finally, we go to message passing. All these first three models are for shared memory using immediate snapshots and possibly k-set agreement. And then we discuss the message passing systems. And finally, the last topic which we address is the topic of decidability. Decidability is a critical thing in computing. Yeah, sometimes you can say that an algorithm exists, but you may not have necessarily an algorithm that finds an algorithm for the solution. Okay, it's a thought to think about. Yeah, it's something conceptually important. You may say that something exists, but you may not be able to construct it. Not all proofs are constructive, especially in computing. Yeah, you might not have an algorithm saying that its specific task is solvable in a specific model of computation. You may have some variants of these questions can be decidable. For example, you restrict your model of computation to its subset. And then sometimes you can have an algorithm saying, okay, give me a task defined as a tuple input complex output complex delta. Give me a model, and I give you an answer, yes or no. If the model is coming from a specific subset of models. Or you fix the model and you fix the set of tasks. If the task is coming from a set of tasks, specific set of tasks, I may be able to say yes or no. But in general, if someone comes to you and says, oh, I have an algorithm that allows you to decide for any task and any model where the task is solvable in the model, you can immediately say, no, this is bullshit. This is not going to work. And there is a proof that this question is undecidable. Because for any, actually, the proof is quite straightforward, but it's still considered for any three-process shared memory model, there is a task. Well, and for any decision procedure, there's a task which is not, which cannot be decided. So it's a contradiction. Well, we'll come to this. Okay, how much time we have? Yeah, I guess we will have exactly enough time to cover the T-resilient case. And we call the models. We call the basic notions of combinatorial topology and the distributed computing models. So again, skeleton is something if it's half a complex. Skeleton of dimension 2 is all, if you have this solid tetrahedron, which is a three-dimensional simplex with the interior. We take the interior out, we have a two-dimensional skeleton. It's all the combination of all two-dimensional faces of this tetrahedron. Skeleton of dimension 1 is all a collection of all the edges, and the set of vertices is skeleton of dimension 0. Okay, skeleton of dimension 0 is just the set of vertices of a complex. What we're gonna do is something like this. So it's gonna be common for all characterizations in all the models we're going to consider. We identify for each model, we identify some specific parameter, which varies from 0 to n. We only deal with models of n+1 processes. Yeah, all the simplices in the protocol complex of the model we consider as dimension at most n. Okay. We identify this parameter p. What does it give us? We are going to claim that a given task, like input output delta, as a protocol in this model, if and only if there is a continuous map from the skeleton of dimension P of the input complex embedded in space, geometric realization of the skeleton of dimension P, to the geometric realization of O, of course, carried by delta. Yeah, it's not because the continuous maps always exist. Give me one space, give me another space. I can always find the continuous map mapping one to another. Yeah, just map everything to one point. It's a continuous map, but it has to respect the task. So to make it non trivial, add carried by delta. Okay. So this is going to be our model characterization theorem. All the theorems we are going to prove are going to be of this kind. So the only interesting point here is what exactly is this P? How you identify the P? So this parameter P depends on the model. This is where I just write it explicitly. This is where the model matters. How we define P. Otherwise, you see that there's nothing about computing. Everything is about existence of continuous maps between some spaces. And this is the task, right? There's only task. Task is defined by three abstract objects.
I don't see what you're writing. I'm looking at the slide now.
You don't see what I'm writing, strangely. Let me share my screen again.
Yeah, what's my screen's the slide?
Strange. Give me a second. Okay. Do you see it now?
Yes.
Yeah. So this is where. So yeah, this part of characterization is defined by the task, entirely by the task. So the only point where the model matters is this parameter here, which defines the dimension of the skeleton. Now let's think about it for a while. You see, P varies from 0 to n. Yeah, we only deal with skeleton of dimension n of I. So if P is n, then we didn't change anything. Yeah, we deal with a large map. The higher is P, the larger is the space, skeleton P of I, embedded in space. Yeah, the more points it contains. The smaller is P, the smaller is the space. Now, it is always easier to find a map carried by delta defined on a smaller space. Yeah, because we need to take care of less points. Okay, doesn't make sense? Yeah, it's always easier to define a continuous map satisfying some properties on a smaller set of points. Yeah, because if you define it, if you extend it on a larger set of points and also satisfy some carried by delta requirement, you can always restrict it. Yeah, so you can restrict it to a smaller set of points. If you have define f on skeleton, I don't know, P of I, yeah, embedded. You can always restrict it, get f prime defined on skeleton P prime of I for any P prime less than P. Yeah, but not vice versa. It's not always easy to extend the map. Yeah, so you have a map defined on a subset. To extend it to a larger subset is difficult, and sometimes it's impossible. Yeah, remember the definition of connectivity. Sometimes you can extend a sphere to a disk. Sometimes you cannot, when the destination space is not sufficiently connected, right? So this is the tricky part. So now coming back, so P equals n, nothing changes, because you dealt with the original skeleton of dimension n. Now you have to deal with it again. P equals 0. What does it mean? What is this zero skeleton of I? Instead of vertices of I. Vertices of I mapping continuously and carried by delta is trivial. Individual vertices, any map of vertices to O is continuous. Why? Because vertices don't have no neighborhoods. What makes it difficult to map for a continuous, create a continuous map is you have to deal about the neighborhood. You need to make sure that if I map a vertex to something, arbitrarily small neighborhood, it should go to some small neighborhood of the codomain. And this is not always easy. If there are no neighborhoods, nothing to do. Every map defined on vertices is continuous by definition. And now what I can do is to map it to some vertices which respect sigma, or respect delta. So it's carried by delta. So I can always find such a map. Okay, trivial. So trivial to solve any task. Okay, so on one extreme, the model is the same as read-write models. It doesn't give us anything. On the other extreme, it gives us everything. And the interesting cases are in between. Okay. Yeah, so again, so dimensional skeleton versus computational power. If you have two skeleton map is harder than one skeleton map. Yeah, you can see that. For example, this is exactly what I was saying. The connectivity is defined on the sphere, extended to a disk, but sometimes it's not possible to extend. There exists a continuous map from a sphere. So this is a one-dimensional sphere. And you have a continuous map which maps this triangle here to this I don't know, circle here. But you cannot extend it to the map from two-dimensional disk to the interior of the sphere. Okay. So it just illustrates the fact that you can always restrict a map to a smaller domain, but you may not be able to extend it to a larger domain. Okay. So up to n out of n plus 1 can crash. The regular immediate snapshot model, layers. Every time you reach a layer, you write and take a snapshot. What do you do next? Yeah, well, if you assume that nobody is guaranteed to be correct, like everybody can fail. Now, up to n can fail. Basically, you cannot wait for anybody. If you start waiting, you can be waiting forever because you may be the only one who is operational. Yeah, so now the task has a wait-free protocol if and only if there is a continuous map from the skeleton of dimension n to O. This is what we already proved, right? It's a colorless task. We talk about only colorless tasks. Okay. This is called wait-free, by the way. This is a wait-free model. Yeah, I used this term already before, and I think I informally defined it, maybe even formally, some time ago, a few weeks back. But the notion of wait-free is basically what we call n-resilient or n plus 1 process. Everybody can fail but one process. Why but one? Because if everybody fails, it becomes trivial. Nobody needs to produce anything. So we ignore the executions in which everybody fails, because in these executions we don't guarantee anything. Nobody has to decide. Nobody has to produce an output. Okay. So you can see that this statement is like the statement we defined before, but with p equals n. So this characterizing parameter for the wait-free model, for the immediate snapshot model, in which out of n plus 1 processes up to n can fail, has the characterizing parameter n. Yeah, so you see the characterization has the same structure as we just defined before. Okay. Very better, of course. T-resilient. I will formulate the theorem. We will prove it next time. And next time is going to be in 2 weeks, because next week you have this formation humaine. So yeah, I would actually encourage you, everybody who's here and who is not here, to look at the exercises, try to solve the exercises, because I think this will help you to understand a lot. And also submit the exercise solutions for the previous lecture, for the colorless tasks. Right, so we have T-resilient layered immediate snapshots up to T out of n plus 1 now crash. So before we had up to n out of n plus 1, now up to T. T is possibly less than n. Okay. it's okay to wait until n minus t plus 1 would move, right? Because up to t can fail, you have n plus 1 processes, at least n plus 1 minus t should be correct, should take steps. You know, the characterization is that you have a t-resilient protocol for a task, even only if there is continuous map from skeleton dimension t now. Yeah, so now the parameter p is equal to t. So the smaller is the t, the more powerful is the system, right? In the extreme case of t equals to 0, you have skeleton of dimension 0, which is a set of vertices of I, and the map carried by delta can be easily constructed. We will see this next time. Okay, but keep in mind that we have the same structure of the characterization of t-resilient model, except that we replace the parameter p, which is abstract parameter for model, with a concrete number t, which is the resilience level of your model.
Yep. Just a small question.
Yeah.
What do you mean by a more powerful protocol there? Because as I understand, with n processes crashing, you have skeleton of n of I. You need to have a continuous map with skeleton of n, which is bigger or equal than any other t. To me, it seems like a protocol solving weight-free is stronger than any other protocol for
no, I'm not talking about a stronger protocol. I'm talking about the power of the model. The model, the stronger is the model, the more tasks it allows for solving. Weight-free model has very little tasks which can be solved.
I see. Yeah. Now I see. Okay, in the extreme, no process can fail because t is 0. Okay.
Exactly. Yeah. If t equals 0, it means that nobody fails. You can solve any task.
Okay.
This is the most powerful model you can think of. Yeah. And the other extreme is weight-free. This is the weakest model you can think of because there's very few models, very few tasks, and these are the tasks of the type of epsilon agreement. Yeah, this approximate agreement at best. This is what you can solve. Like even set agreement can be solved. A set agreement is already something deterministic. You have n plus 1 inputs, you get rid at least of one of them. Yeah, so it's and even this cannot be solved. With t equals 0, you can wait for inputs of everybody and just deterministically map it to the output. Because everybody sees exactly the same set of inputs. Just choose some simplex in the output complex and be done with it. Okay. Right. I will stop here. Any questions? Everything is clear? Not clear? You're completely confused? So what I would suggest to do is to look at the exercises. I would also suggest this way. If you find the exercises difficult to understand, maybe you don't understand what you asked to do, raise a question in the forum on the campus. That would be probably the best way to interact. So you're confused, ask a question like explicitly on the campus in a forum. We can discuss it. You can also look at the questions raised before. So there were some discussions earlier, which is quite interesting. And, so that may help also. Okay. So unless you have more questions, I will probably stop here. So let me quickly stop recording.